Hey everyone, this is the solution video for the reading quiz on June 3rd. Let's start with question 1. So question 1, we have an 8-kilogram crate, and it's being pulled by two people, each pulling on a rope attached to the crate. So let's sketch this. Here's our 8-kilogram crate. Damn autofocus. There we go. And we have angles involved, so let's draw a horizontal x-axis so we have something to refer to those. Okay, so the first person is pulling at an angle of 30 degrees with a force of 30 newtons. So let's call this force F1, and that's 30 newtons. And the angle we'll call theta 1, which is 30 degrees. And then we have the second person pulling at an angle of negative 70 degrees. So it's going to be something like that. Call that theta 2, negative 70, and F2 is 40 newtons. Okay, so this should be pretty straightforward if you remember how your vector components work when you're adding vectors. We want to find the net force. So the components of the net force are going to go like this. The x component of the net force is going to be the x components of force 1 and force 2. And the y component of the net force is going to be the sum of the y components of force 1 and force 2. And we should know how to get those components just from our basic vector stuff. So then F net x is going to be F1 cosine theta 1 plus F2 cosine theta 2. So let's see, we've got 30 newtons times the cosine of 30 degrees plus 40 newtons times the cosine of negative 70 degrees. And adding those all together, we should get, let's see, 39.7 newtons. So that's the x component of the net force. The y component is similar. Instead of cosine, we use sine. Move this to the side. Push my mouse out of the way. So F net y is going to be F1 sine theta 1 plus F2 sine theta 2. And that's going to be that same 30 newtons times the sine of 30 degrees plus 40 newtons times the sine of negative 70 degrees. And doing that out will give us negative 22.6 newtons. So those are our components of the net force. And then we want to find the magnitude. So remember, the magnitude is just what we get when we square each component. I just call this just F net x squared plus F net y squared. We square each component, sum them, and take a square root. This actually has a term. This actually has a technical term to describe this procedure. It's called adding in quadrature. Anyway, when we do that, let's see, we'll plug everything in. 39.7 newtons squared plus negative 22.6 newtons squared. Square those, sum those, take the square root. And we get a net force magnitude of 45.7 newtons. Okay, so the net force is going to be 45.7 newtons. And what's the direction? That brings us to question number 2. We want the acceleration of the crate and the direction it starts moving in. So the acceleration of the crate should be pretty straightforward. That's just Newton's second law. Newton's second law is F equals ma, specifically F net equals ma. We've got F net, we've got mass, so we should be able to solve for a to find the acceleration. And that should be F net over the mass of the crate, which we found, let's see, 45.7 newtons divided by 8 kilograms. So that gives us an acceleration of 5.71 meters per second squared. Oh, my cat's trying to get in the door. If you hear any meowing or weird noises, he doesn't like the door being closed. And the angle at which it's going to act is actually the same as the angle which the force is going to act. So we don't need to calculate the components. I'll write that down. We don't need to calculate the components of the acceleration vector here. It'll be in the same direction as the force, which we have the components for. So theta is going to be the arctangent, or the inverse tangent, of F net y over F net x. So let's see, F net y we already found to be negative 22.6, and we found F net x to be 39 point something, 39.7. So if we divide those into each other and we take an arctangent, or an inverse tangent, we get an angle of theta equals negative 29.7 degrees. So if we go back to our original sketch, that tells us that the crate is going to accelerate roughly in this direction, or so. Which makes sense because this person is pulling harder than the person pulling that way. All right, question number 3 and question number 4 are pretty closely linked, so let's see if we can do them in one segment of the video. All right, so question 3 starts with a car massing, looks like 1,100 kilograms. We'll write it out in scientific notation to preserve our significant figures. And it's traveling at, call this v sub I, traveling at 30 meters per second. And the driver sees a deer jump onto the highway ahead, and she hits her brakes. And the brakes exert constant braking force of 4 kilonewtons. Now 1 kilonewton is 1,000 newtons. Oops. So we could just as easily write this as 4.00 times 10 to the 3 newtons, or just 4,000 newtons, but this preserves our significant figures better. Okay, and we want to figure out what the deceleration of the car is in meters per second squared. So let's draw this real quick. Here's our car. I'm not a great artist, so bear with me here. And it's going at 30 meters per second. Then it applies a braking force, and the braking force is going to act opposite to the direction of motion. So when I say a braking force, what we should really do is stick a negative sign on this force. So the force is actually going to be negative 4 kilonewtons. With that in mind, we can now work out what the acceleration is just using Newton's second law. Okay, so F equals ma. In this case, the only force we're interested in is the force in the x direction, which is just the braking force. So we have F equals ma, which we can solve for a. And here we have negative 4,000 newtons. And we have the mass of the car, which is 1,100 kilograms. And so we should find the car's acceleration to be, or deceleration, I guess, to be negative 3.64 meters per second squared. Okay, that's pretty straightforward for question 3. Now, question 4 wants you to figure out how long is it going to take the car to stop? And so we actually need to use our kinematic equations for that. So let's put this paper to the side and start on problem 4. So problem 4, we want to find stop time. Call that t-stop. This is also pretty straightforward. We have an acceleration, we have an initial velocity, so and we know what our final velocity is going to be. It's going to be 0 because the car is coming to a stop. So let's write down what we know. We know a equals negative 3.64 meters per second squared. We know vi equals 30 meters per second. And we know vf is going to be 0 because we want the car to come to a stop. So let's use our velocity kinematic equation. And that's just vf equals vi plus at. And we can solve for t. So solving for t gives us t equals, let's see, vf minus vi over a. So that should be pretty straightforward. Plugging in, we get 0 minus 30. I'll put units on that so it's a little clearer. 0 meters per second minus 30 meters per second divided by our acceleration, which we already found to be negative 3.64 meters per second squared. And doing out that calculation, we should find the car takes approximately 8.25 seconds to stop. All right, number 5. Number 5, we have a 15-kilogram box, and it needs to be slid up a ramp inclined at 30 degrees. So here's our ramp. Let's say 30 degrees there. We have our 15-kilogram box, which is sitting on it. And we want to find the force in newtons applied parallel to the ramp that is needed to accelerate the box up the ramp ahead of acceleration of 1.20 meters per second squared. So to make this slightly easier, let's try drawing a free body diagram with the box. I'll just go with this sketch. So here's the force we're going to apply. Call that F sub app. Then we have the normal force in the box. Remember, the normal force is actually perpendicular to the surface it's on. It's not going to be straight up anymore. Then we have what we'll call the the perpendicular gravitational force and the parallel gravitational force, which acts down the ramp. So the box isn't going in or out of the ramp. It's not flying up off it. It's not crashing through it. So we can just assume that the perpendicular forces, the net perpendicular forces we'll call it, are 0. That the normal force exactly cancels out the perpendicular force of gravity. We know that the perpendicular force of gravity is negative mg cosine theta, where theta is the inclination of the ramp. And so in order for this to be 0, we then know that the normal force is going to be mg cos theta. So F perpendicular net is just mg cos theta plus negative mg cos theta, and therefore 0. Now for the parallel forces, that's where we need to work out what our forces are going to be and do some calculations. So let's write down all the forces acting in the parallel direction. Parallel net is going to be, let's see, we have our applied force pushing up the ramp, and then we have our parallel component of the gravitational force pulling us back down the ramp. So let's see, we don't have an expression for F applied other than just F applied, but we do have an expression for the parallel force of gravity, which is going to be negative mg sine theta. And then F parallel net we can actually rewrite as ma, technically a parallel. So we have everything we need to work out what F applied is. F applied is just going to be ma plus mg sine theta. So let's substitute everything in there. Let's see, we know the mass of the box is 15 kilograms. We know the acceleration we want is 1.20 meters per second squared. And then we have the term for the parallel force down the ramp, which is, again, the mass. The acceleration of gravity, 9.81 meters per second squared. And then the sine of theta, which is 30 degrees. Sorry, I ran out of space on the page a little bit there. So doing all those multiplications and additions out, I find a force of 91.6 newtons. I believe I had a slight error in my original solution. I corrected that while the quiz was still live. If you got it wrong, I went through and checked and made sure that if you actually got 91.6, it was marked correctly. So if I missed that, let me know, but I think I got everybody. So that's how we do number 5. And finally, number 6. A similar problem, another inclined plane problem, where we have a sled that has a mass of 5.80 kilograms. It's being pulled up a snowy hill. Here's our snowy hill. Here's our 25-degree angle. And here's our sled. Again, I'm a terrible artist, so apologies if this is incomprehensible as a sled. And it has a mass of 5.8 kilograms. Okay, so again, we can draw a free body diagram to figure out what forces are acting on it. So like before, we have our normal force and our perpendicular force of gravity, and they cancel out exactly. So that the net force perpendicular to the ramp, or to the hill in this case, is just 0. I already showed that last time, so I'm not going to do that again. But now we have to worry about what our applied force pulling up the hill and what the parallel force of gravity trying to pull us back down the hill, there we go, are. So in this case now, we actually have the applied force, and we want to work out what the acceleration of the sled is. There's a typo in the quiz. It should read sled, not block, but that doesn't change anything else. We want to find out what the acceleration of the sled is, given that applied force and given that mass of the sled. So again, let's write down our parallel force or our net parallel force. That's going to be the parallel force of gravity plus the applied force being pulling it up the hill. So let's see here. Force of gravity, parallel force of gravity is going to be negative mg sine theta plus our applied force, which we already know to be 32 newtons. I'm not going to write that in yet. I'll just keep that as F applied. And then our net is going to be ma parallel. So the acceleration parallel to the ramp, or acceleration up the ramp. So now we want to solve for a. And doing that is pretty straightforward. We can just divide through by m. So the parallel acceleration, or the acceleration up the hill, is going to be negative g sine theta plus the applied force divided by the mass of the sled. So we can plug everything in to work that out. We'll have negative, then we have 9.81 meters per second squared. We have the sine of 25 degrees. And then we have our applied force, which is 32 newtons, divided by the mass of the sled, which is 5.8 kilograms. And when we calculate that out, we should find an acceleration up the hill of 1.37 meters per second squared. All right, that's it for quiz 6. The quiz on June 3rd. I'll be doing the video for the quiz on June 8th shortly.